Chapter 2. Primitive Notions and Field Fundamentals. 2.1 Static and Stationary Fields. If a field is unchanging over time, it is static. A one-dimensional static field is a real function, and a 2D static field will be shown to be equivalent to a specification of a complex function. If a field or flow is changing but does so at a fixed or steady rate, then it is said to be stationary. A 2D integrable flow can, again, be represented using complex functions. By starting with a field or fluid that is static or stationary, we've effectively carried over the inertial concept from point-particle dynamics first. Recall that Newton's second law F equals ma is simply F equals 0. So, no force if motion is static or stationary, A equals 0. If no force, the system is unchanged in its motion, fixed or linear. We will start in section 2.2 with complex functions as fields to elaborate further.
2.2 Complex functions as fields. A complex function can be viewed as a mapping from a complex number, a point in 2D, to another complex number. For a well-defined limit process on such a mapping, the components of the complex number must be potentials satisfying the Cauchy-Riemann equations, or related 2D Laplacian, with whatever boundary conditions are indicated. One might ask, can quaternions be used to map a point in 4D to another in 4D? There are a variety of constructs where this is possible, but even more interesting, some are Lorentz invariant, and describe 4 vectors. This connection to Lorentz invariance, the topic of Chapter 8, is easily overlooked as a mathematical oddity at this stage if there wasn't more to it. As described in Appendix A, the Cayley algebras consist of algebras starting at 1D, the real numbers, and doubling in dimensionality for each new algebra, in effect, due to an added layer of complex structure. After the real numbers come the 2D complex numbers, then the 4D quaternions, then the 8D octonions, then the 16D sedenions, then the 32D trigentillionians, etc. Thus, it would seem we can describe an infinite number of mapping processes from 2D 2D, 4D 4D, 8D 8D, etc. It turns out, however, that the mapping is assumed to have an inverse, or no zero divisors, thus must be what is known as a division algebra, and the highest order Cayley algebra that retains this property are the octonions. So let's go one step further than the aforementioned quaternions and ask, is there an 8D octonion mapping that is also Lorentz invariant? The answer is yes.
Suppose we don't want to be stopped so easily by the aforementioned division algebra constraint, and consider a biquaternion instead, dimensionality like an octonion since 4 plus 4 is equal to 8, and add complex structure, equivalent to all components generalized from real to complex, such that we have an object with the dimensionality of a sedenion 16D, but with the switch from a Cayley product rule to a split product rule, the products devolves to 2 octonion-like products, each with inverse, thus with overall inverse. Now, with this ridiculously large 16D object that is split, can we again arrive at a Lorentz invariant construct? The answer, remarkably, is yes, and this has been known since 1917. Can we go to higher, even higher order using split Cayley algebras? Evidently not, and this and other features are discussed in Book 7 on emanator theory, where such maximal mathematical objects are the basis for a theory of maximal information emanation. Well before getting to hypercomplex numbers and their potential applications, however, regular 2D complex numbers will already have earned their primary place, from efficient computational methods using complex functions and the Schwarz-Christoffel transform, to providing mathematical hints at how to deal with singular sources. Some of the key properties are outlined next, with further background in Appendix A.
Let's now consider functions of a complex variable. Implicitly, this means we have a complex number that is the value of a function of complex number, i.e., we are mapping from a complex number to a complex number, from 2D to 2D. Due to the richness of the complex numbers mathematically, the variety of such mappings that are possible is its own area of study that will only be mentioned briefly. See Appendix A for further details and references. This is notably different from the quaternions and higher Cayley algebras where there is nothing similar, and at its root it is because the notion of derivative only extends to complex functions and in a special way, fully specified in the free parameters introduced, while extensions beyond, to quaternions and higher, fail due to overspecification of the free parameters, thus no non-trivial solutions possible. Let's examine what makes complex functions so special. Suppose we have f of double struck : the complex numbers double struck goes to the complex numbers.
Equation 2-1. The definition of limits and continuity are as expected and are given in detail at reference 23. For a definition of derivative at a point, we generalize from x times epsilon the real numbers to z times epsilon the complex numbers with equation 2-2. For this to be meaningful, however, it should not depend on how the limit is performed. If we let delta z equals delta x comma delta y tend to 0 horizontally, delta x comma 0 to 0 comma 0, we get for f equals u plus iv. See the next equation.
If we let delta z equals delta x comma delta y tend to 0 vertically, 0 comma delta y to 0 comma 0, we get. See the next equation. These two limit expressions for derivative must be in agreement if the definition of derivative is to be well defined. Thus, for the complex derivative of a function to exist, its components must satisfy equation 2-3,
which are known as the Cauchy-Riemann equations. As can be seen, the function constraint for a derivative to exist is significant. We will explore next what complex functions are differentiable, but before moving on, note how the system could easily be overconstrained when going to quaternions and the higher-order Cayley algebras. Thus, we lose the critical derivative variational mathematical tools when going to higher-order Cayley algebras. This is consistent with the fact that only the complex propagators can satisfy the quantum de Finetti relation, since the quaternion and higher-order propagators would be overly constrained in that situation as well. We thus see maximal information flow in terms of projections of Cayley algebras, which must eventually reduce to a representation of propagators in a complex Hilbert space with complex propagators. We will describe maximal information flow in Book Point 9. Typically, we want to work with functions that are not only differentiable at a point, but in the neighborhood of that point. In the context of the complex derivative, this is a more involved mathematical construct, since the Cauchy-Riemann equations must then be satisfied on the domain neighborhood indicated. When this is the case, the function is said to be analytic holomorphic on the indicated domain. If a function is analytic on the entire complex plane, it is called entire. If a function is analytic on a domain, then rearrangement of the Cauchy-Riemann equations shows that the component functions are harmonic, satisfy Laplace's equation, in the domain.
Equation 2-4. If a function is analytic everywhere except at an isolated point z sub 0, i.e. it is analytic in every neighborhood of z sub 0 but not at z sub 0 itself, then z sub 0 is called a singularity of the function. An example of this is f of z equals 1 divided by z. The management of singular items in the 2D complex mapping will provide critical developments for 3D field theories, where there are point particles with singular potentials. Let's now turn to complex integration, or antiderivative. As might be expected, the integration is no longer defined on an interval on the real line. It is now generalized to being defined on a curve in the complex plane, i.e., we have the line integral. The line integral concept is then developed further, in 3D, in vector calculus introduced with EM. Let's compute the line integral for polynomials for the closed curve shown in Figure 3.1.
Figure 3.1. Line integral for the unit circle. The curves are specified by script c sub 1 colon z equals e raised to the I theta power for 0 is less than or equal to theta is less than or equal to pi, and script c sub 2 colon z equals e raised to the I theta power for pi is less than or equal to theta is less than or equal to 2 pi. Let's now consider integrals of the form. See the next equation.
Case 1, f of z equals 1. See the following group of equations. Case 2, f of z equals z. See the following group of equations. Case 3, f of z equals z squared. See the following group of equations. Clearly, for f of z equals z to the nth power for n is greater than 2, we will also have I equals I sub 1 plus I sub 2 equals 0. For negative integers, this relation will also hold, except for n equals negative 1.
Case 4, f of z equals z to the negative 1 power. See the following group of equations. We have arrived at the residue theorem. See Appendix A for more detail, where we express any function as a Laurent series. See the next equation. The integration of that function on any closed curve about the origin is then I equals the contour integral from script c2 of f of z dz equals 2 pi I a sub negative 1. The coefficient of the 1 divided by z term in the Laurent expansion, a sub negative 1, is the only term with non-zero contribution, referred to as the residue. It appears that any complex function that is analytic throughout the region interior to a closed line integral will have result of 0 for that integral.